So next, let's do problem 14. We have, let's see, v is conjugate to u, all right? So then the big U and big V are independent of path. That's the first part of the problem. And then secondly, big V is conjugate to big U. That's the part that I didn't see, okay, and skipped. So, but I got it done just now, so then we're good. So then if V is conjugate to U, which means by earlier definition, U1 equals to V2 and U2 equals to negative V1. And so we got to first show that U, as defined that way, is independent of path, which is also means that U is well defined, because and so is V, of course, because if it depends on how you integrate to get the answer, then each U has various different answers, right? So you can't get it to come out. Now being well defined for a function needs to be well defined, because just because you call something a function doesn't mean it makes any sense. For example, if this is not independent of path, if this value depends on how you got from a to ab to xy, then your uxy isn't a function, because a function needs to be something that crank out one value. Okay, and if it cranks out a whole bunch of values and you don't know what it might be, then you don't have much of a function. So this, if this is independent of path, that means that U is a well-defined function as described this way. And similar, the same thing for V. Now to show that U is independent of path, we remember this relationship right here, okay? And then we'll let the P part, which is P equals to U, and Q part will be equal to negative V. And then we notice that P2, which is U2, which is negative V1 right here, and which and then Q1 is negative V1. So that is just U2, which is P2, and Q1 equals P2, which by theorem 5, that means this thing is independent of path. I should also show you theorem 5. So here is theorem 5, where we have the functions. You notice that if functions are reasonably, when Q1 equals to P2, and then the integral is independent, the integral over here, okay, integral 1 on, I think this side, yeah, this is integral 1. This integral 1 is independent of path, okay, with these reasonable requirements. That's theorem 5. And so then by theorem 5, we have proven this is independent of path as required. Then the other one, the V function, works exactly the same way. For the V function, we have, now for the V function, we have, for example, that, let's see, let's see, what is that? Okay, for the V function, we have exactly the same thing. We have end up P is V, Q is U, and do the P2, which is V2, which is U1, which is Q, and by the same theorem 5, the V is also independent of path. So those are easy enough to do. But however, the next part, it says that we need to show big V is the conjugate of big U. Or in other words, we need to show that U1 equals to V2 and U2 equals to negative V1. That is the definition of the conjugate, I think. Let me double check again. In problem 9, that function V such that U1 equaled, if given a function U, if we have a function V such that U1 is V2, U2 is negative V1, then the function is said to be conjugate to U. So we just have to show those two relationships, which is not that obvious, because so far we have done the integration. If you let's look at page 228 again. Okay, the equation 1 that we have seen just a little while ago, where the function big F is defined on x0, y0, right? And then you integrate from AB to x0, y0, and then P dx and Q dy, where the things in here are the dummy variables, or anyway, so we're doing x0, y0. Now in the homework, you notice that there's no x0, y0 anymore. For example, consider problem 4. We have We just have xy on top of the integration, okay? Which we sort of just pretended that xy here is x0, y0, and we went ahead and did the homework anyway. So we did okay before, like in problem 4 without too much trouble. But now we have to show that u1 equal to v2 or whatever. What that means is that we have to take the derivative with respect to that thing on top. With the variables in here, that's the same. That looks the same. So we have to remember that they are not the same, okay? And with that in mind, so what I'm gonna do is just write out a different situation. That is, we'll let axy equal to the indefinite integral of u dx. That is the first part of the equation. And being that u was, well, anyway, so then if this is the case, then the function is, well, that's just the indefinite integral, okay? And that's all it is. So I'll define axy equal to indefinite integral of u xy dx. Now, let's not worry about the constant for now, because we're going to be taking derivative of these things. Then a1 is going to be u xy. Because we're taking the derivative with respect to x. So with the integral, and then you take the derivative, you just get u back, right? And similarly, bxy will take it as the indefinite integral of vxy dy. And so then if you take the partial derivative, the second derivative, that will just give you back vxy. Similarly, for c, I'll define it as the integral of v dx, and d will be defined the integral of u dy. So then c1 is going to be v, and d2 is going to be u. So you notice that a1 is going to be equal to d2, etc. So and with that, it's going to help us that's just to help us keep clear of all the variables, who's what, who's the dummy and who's the limit and all those things. Now with these definitions in mind, okay, now please bear this in mind. So I will turn the page. Then uxy, the big U then, by definition, is going to be equal to the axy at the top, okay, minus aab, and minus the bxy, and then minus big B of AB. That just comes directly from the definition. Let's see, how do I hold it? You can see. Maybe I should have printed them out. Now I can't hold them both properly, so you can see the two things together. Or maybe I should have written it out this way. Yeah, it's kind of hard to hold. Anyway, okay, I got this here. Maybe you can take a screenshot of this. So anyway, as you can see here, then by definition, uxy is A evaluated at the limits minus B evaluated at the limits. And similar for vxy, okay, which is C evaluated at the limits and then plus D evaluated at the limits. So now with that should be good. Now knowing that, then we'll do the calculations. So now first we'll take the derivative, partial derivative, the first one, that's u1. Anyway, my kids were yelping for no reason, so I had to yell at them. But anyway, let's move on. Okay, well, what was I saying before? So we calculate u1. Okay, u1 will be a1 minus b1. All the constants here, we ignore them. So then a1 minus b1, and a1 happens to be u, as we have shown before. See, a1 is u, but we don't know what b1 is. There's nothing directly for b1, so I just wrote it down here. And then for v, which equal to the c and then d, evaluated as c and d, and then we take the partial derivative of v2. The reason we're doing this is because right now we're trying to show that u1 equals to v2. So let's crank it up. So v2, taking this stuff, and then in the same way, we end up have c2, whereas d2 equals to u. Okay, from the previous page, where d2 is u, but we don't know what the other thing is. What was the other thing? c2. Yeah, we don't know what c2 is. So we have that thing and that thing. Okay, part of it the same. They both have u in it. So now we need to show that minus b1 had better be equal to c2 for this relationship to hold on. So let's calculate what is minus b1. And we'll calculate b1. b1 is the integral of v1 xy dy. Right, that is because B1 is, let's see, B is defined as this, okay? B is the integral of v dy, so B1 will just take the derivative of inside the integral, and you're allowed to do that. So then we'll take the derivative inside the integral, it becomes V1, and then we'll interchange. Remember, from the previous page, the small v1 is the same as negative u2. We said that earlier, okay, right here. Small v1 is negative u2, so we plug that in, and then once we have that, now we're integrating u2 with respect to y. That means that just cancels out by the fundamental theorem, and the fundamental theorem, as a result, we have just minus u here. There's nothing here, I just, yeah, it's just minus u. And similarly for C2, which is, we define it as V2, which V2 is just U1, okay? And then, which is given. Now, it's, U2 equals to, V2 equals U1, integrating this U1 with respect to X, also give us U back. This means that B1, negative B1 equals to C2. And as a result, then we got it down, okay? That's what we were setting out to do, U1 equals to V2. Now the second part, showing the V part, the U2 equals to minus V1 works exactly the same way. So please read that yourself, okay? If you have any questions, or just work it out exactly the same way. And with that, and then that will come out that U2 equals to negative V1, and that should be it. And together, these two parts forms the entire proof, which I had to scratch out a bunch of junk. But you get the idea. The part of it is the part that you should pay careful attention to is just the notation business, okay? The dummy variable versus the variables in the limit. You just have to think very clearly and keep everything straight. And also the, what was the other thing? Oh yeah, the partial derivatives. That you can take the partial derivative is into the integral, especially because you had the partial derivative is you're taking the derivative with respect to the variable that isn't being integrated. Like this one. See C2. When I take the partial derivative in here, I'm you notice that we're taking the partial derivative with respect to y, whereas the integral is only doing x. So then the partial derivatives carries through without too much of a headache. So okay, so that marks the end of this section.